In the previous video, we looked at what a vector was, right? And the basic just characteristics of vector, how we add vectors. And we looked at the notation A to B like this, which just means how do we get from A to B? Now this particular vector is known as a direction vector because as it suggests, it tells us the direction from A to B. There's something also called a position vector. And this is also technically a direction vector, but it's a direction relative from the origin. So if I was to draw a graph like this, I'm going to label 2 points A here, and I'm going to label this point here B. And so this is O, right, the origin. So O to A would represent a position vector, because it's a position relative to the origin. But it also allows us to see where it is, or how we get from O to A. So it's also known as a direction vector, but we just call it a position vector. Same thing with A to O to B. This is also a position vector. However, A to B is a direction vector because it's not relative to the origin, it's just relative to each other. It's saying, well, how do I start from A and how do I get to B? And so that's why it's called a direction vector. And in order to find this, let's say we know O to A is A, O to B is B, right? To find A to B, what we have to do is we go A back to O, and then we go O to A. So essentially it's just saying, well, it's minus A plus B like this, okay? And so if you're asked to find A to B, it's just essentially, you just have to think of it as going B minus A essentially. Okay? That's how you normally find a direction vector. Same thing for for example, if there was a C, like A to C, then it's just gonna be C minus A like this. Okay? So make sure you understand the difference between a direction vector and a position vector. All right, so let's take a look at this example here. So we have the position vectors of 3 vertices of a parallelogram. And these are 4, 2, 3, 5, and 8, 6. Find the possible position of the fourth vertex. Okay, so let's just, for vectors, I recommend drawing a graph. It's just to visualize, or it just allows us to see a visual representation of the question. Right, so we have 3, 4, 8, and we have 2, 5, 6. So we're going to have 1, which is going to be 4, 2 here. We're going to have 3, 5, and we're going to have 8, 6, like this. Okay. Right. So it's a parallelogram. So they're asking us where is the fourth vertex. So we have to, as we said, you can imagine where it's going to be. Let's call this one A, B, C, D. So we're trying to find D. So A is 4, 2, B is 3, 5, and C is 8, 6. So if I was to visualize it, then, well, parallelograms means they have the same, two of the lines are parallel, right? So if I were to draw a line here and connect these two like this, then there has to be a line which is parallel to this one and parallel to this one as well, right? So the vertex would be roughly, the D vertex, one of the possible positions would be here. So that way it's parallel to here, and it's also parallel to these like here, right? So we're trying to find this D positioning here, okay? So it's all about position vectors and direction vectors. So these vectors here we're given, they're all position vectors, i.e. they're relative to the origin. So we have to think of how do we get to D? Well, let's start off at A. So we're trying to find A to D, right? Well, we're trying to get to D. Well, let's say O to D, okay? Because that's the position vector we're trying to find. How can we get from O to D? Well, we can go from O to A, and then we can go A to D. That way we end up at A to D, or O to D, right? And so O to A is just simple. O to A is just the position vector of A, which was 4, 2. It's just A to D that we have to find. But the thing we know is that A to D and B to C are actually parallel to each other because it's a parallelogram, which means they are actually the same vector. So all we need to find is the vector B to C, and that will be our A to D. So B to C, as I said, is the same thing as C minus B, the position vector of C minus position vector of B. So C is 8, 6 minus 3, 5. So this is going to be 5, 1. So this would be the direction vector B to C, which in turn is the direction vector A to D. So we just have to plus 5, 1 to here to get the position vector of one possible answer for a vertex of D would be 9, 3 like this. Alright, so that's one possible solution. We just have to find the second solution. So if I just get rid of these for now. So let's just connect some other vertices. So if I connect this one here and this one here, that means that these positions should be roughly here, right? Because now this is parallel, this is parallel, this is parallel. So now we have to find this D position here. Okay, it's the same situation. You have to find an initial root that we have to get to, right? So O to D. So how can we get from O to D? Well, I can go O to B, and then I can go B to D. Okay, so take this part here, right? Because we know O to B. So O to B, we know from earlier, was 3, 5. Then it's just a matter of finding B to D. As you can see here, B to D is parallel, i.e. the same as A to C now in this case, because these are the parallel lines together, right? So we just have to find A to C, and A to C, as I said earlier, was just C minus A. So 8, 6 minus A is 4, 2, which is 4, 4. So that's A to C, which in turn is B to D. So I just have to write 4, 4 like this, which will give me 7, 9 like this. So this is the second possible position of the vertex of the parallelogram. So the important thing I want you guys to understand is how to find direction vectors, and then how to use these direction vectors when they are parallel to each other to find additional position vectors.